Okay, so this is kind of the basics, right? There's problem complexity we know how to solve, which is P, and then this BQP, which is bounded um, error quantum polynomial time. So this yellow area is essentially where algorithms exist that we think are better than what we can do classically in mathematical terms. And there's a bunch of different places that you can go to look up these algorithms and what they do and the different patterns that people use to deploy them and to test them and trying to, again, a lot of this is theoretically, here's what the algorithm does, here's what the speed up could be, and then what you're asking is where can we go apply it, or how do we apply it, or what scenario do we try and use it in? So there's some resources out there that will help you make those connections. I wouldn't necessarily say you're going to invent a new quantum algorithm, but you may say, I'm going to take a classical method and try and use a quantum algorithm in a way that hasn't been used before. And that is the exploration, and that's what we're trying to do as well, is figure out where can these things be used that people haven't looked at before, and is there potential there that no one else has thought of? One of the great things that I heard from one of our early partners, 1Qubit, was they had a whole bunch of smart people, smart mathematicians and theorists and data scientists, and they would give them old math books, and they'd look through all the old math books and say, oh, here's a method that no one uses anymore because it's not efficient on classical computers, but maybe that's something we can use on a quantum computer. And that's how they started to come up with some of their new and interesting algorithms. So I thought that was not algorithms, but new and interesting methods that use quantum lower level algorithms that can be extrapolated up. So this is one way to go research it and look at it. Another view that I'll share, and yeah, so this was just a quick example. So eigenvalue estimation, if you look up, I think this is, I don't know if it's on Patterns or whatever, they have variational quantum eigensolver, and they tell you more information about what it does and how to use it. So another view to think of this is, why use quantum for something? Why do these things? And I like to walk through these examples where we say, here's a lithium, this is actually supposed to be lithium hydride atom. We can take the structure of this atom, and you see there's 4 electrons. And then we look at our quantum chip, and we say, we're going to put these 4 electrons, we're going to simulate those as qubits on our quantum chip. And so you can see directly, this is what exists in the real world. This is what we're going to do on our quantum processor. And we're going to run those simulations to figure out how, simulate how those molecules or how those electrons act in the real world and what their connections are and associations are by changing the energy levels and values within the quantum system. So this is one way to think about how you use a quantum computer. And very quickly, if you look at something like caffeine or something we've been exploring, PFAS, polyfluoride alkaline substances, they're intractable to do classically. You can't compute all the possible permutations of the positions of the electrons of those using a classical computer. So this is why we want to explore quantum technology, and the quality of the quantum chip really matters. So there you see 31 electrons. You would think this would easily fit, and we'd be able to simulate this on IBM's new 400 qubit machine, but it doesn't have the circuit depth we need in order to flush out all of those simulations, right? And so even though the numbers seem to match up, the quality of the system matters immensely for doing these types of simulations. Another way to think about this, so D-Wave with quantum annealing, this is what the chip actually looks like. Well, this is an older chip, but they generally all kind of look like this. There's a bunch of qubits, they're connected in particular ways. And in this, we can think about this chip as an area for, a route planning system, right? So you want to get from one point on this chip to another point on this chip, and there's a bunch of stops along the way and a bunch of constraints. And so you can model that information as a graph, and then, convert that graph onto the chip. It's called the embedding process. So you embed it on the chip, and then you run the annealing process, and it finds the lowest energy state of the combinations of points that you put on there, ultimately giving you the best route. And so sometimes if you visualize what these things are doing, you can come to conclusions about how to use them. And so I mentioned earlier the kidney exchange example. This is what the kidney exchange network looked like if you were looking at all the possible ways that the exchange could happen. Then once you embedded it on the chip and ran the annealing process, you would see that just these possible permutations came out. And then if you just separate those out, you would see, okay, here are the exchanges that we could do in order to get the maximum amount of people kidneys within the network. Now, more about this is it's inefficient to do a exchange of 17 people. And so you just, there's too much risk, doctors won't sign up for it. So like this particular formulation wouldn't actually be an exchange you would do, but you can see how this system would allow you to find out how to get the most people, the most kidneys, and it is something that could work under certain circumstances. For machine learning, which is probably the hardest one to extrapolate out how to use it or what to do, I'll use, here's one example. So SVM is support vector machine. This is a classification type of machine learning solution. So here we have some customers, and we want to determine their affinity. Do they like soda or do they prefer coffee? And the way that you would do this is you would take your unknown customers, you would apply a label, and how do you create this label so that you know what they like? It's called inferencing in the machine learning world. Well, you have a training set, and you take your training data of people that you know either like coffee or like soda, and then you create some system for understanding them, location and age perhaps are the parameters you have, and you create a decision surface. And this decision surface is ultimately what you would use in order to classify new customers. In the quantum world, you can do the same thing, but the decision surface just looks different because it's in quantum space rather than in here in the feature vectors in classical space. And so when you can start to envision what the information, how it's going to be modeled in order to do this decision surface, then you can start to have different ideas about what that can be. And then I have one more. This is another machine learning example for sampling. And so same idea here, we're doing inferencing. We're trying to determine from an image what handwritten digit is it. And there's a deep neural network that is used to analyze these images and then ultimately be able to classify them in the future. And so you start with some type of training set. You would use this gradient descent method on the data in order to build a model that would then you build multiple layers of this model, and it would become your deep neural network. And the way that we do it today is this classical method called contrastive divergence, which isn't efficient to run. Excuse me. It just isn't really very efficient to run on classical computers. And so there's an opportunity to use a quantum computer and embed aspects of this deep neural network on the quantum computer in order to do this iterative training within a machine learning method. And so it would be sampling from the model using a quantum device and then reiterating that information back into the model to make it more efficient. And so it's not, again, a machine learning algorithm. It's a component in a machine learning solution that can aid in the training piece. But ultimately, you wouldn't be using the quantum computer during the inferencing section, which is ultimately where you're collecting new data or testing new data or validating new knowledge. So those are some examples that we use to try and flip people's way of thinking about what is a quantum algorithm, where does it used, or how does it exist, and how does it contribute to something meaningful.